students such as Reba, right, and Surat and Sara, they have already done this. Right, Reba? We did this in last class, right, Reba?
Yes, sir.
Okay, fine. है ना? तो Mariam and Aisha, you just note this down and I will be asking you, है ना? Won't take much time. Now after this, we can see what is the effect of these groups. Okay, what is the effect of these groups?
Sir, do we send the answer in the chat?
No. You just know. Acha, you can tell me also. So tell me for OH, plus M or minus M?
Plus M.
Plus M, right? Because oxygen is the key atom. It has 2 lone pairs. What about NH2?
Plus M.
Plus M due to 1 lone pair electrons. What about CH2 positive?
Minus M.
Yeah, minus M, right? Because the key atom, it has a cation, and that is why obviously it is going to pull electrons. I think we did not write this. This is one case. And what about aldehyde group?
Minus M.
Minus M, because the key atom, it is attached to a electronegative atom, that is oxygen, via multiple bond. Now what about the next one? That is ketone group, CO.
Minus M.
Minus M. Okay. Similarly, you can tell me about the carboxylic acid group. What about carboxylic acid group?
Minus M.
Minus M, right? Because again, key atom attached to oxygen with a multiple bond. What about CH2 negative? What is the key atom here? The key atom is carbon, right? Yes or no?
Yes, sir.
Now tell me, is carbon attached to any electronegative element?
No.
No. Does carbon, that means it is not minus M. Now we have to check whether it is plus M or not. So does it have lone pair?
Yes.
Right. So if it has lone pair, that only then it will be plus M. Okay, only then it will be plus M. What about OCH3?
Plus M.
Plus M, right. This will be also plus M. What about C double bond O ester group? This will be minus M, right? Because carbon is attached to oxygen, which is an electronegative element, via multiple bonds. This will be minus M. What about nitrile group? Plus M or minus M?
Minus M.
Minus M. Okay. Now, what about this group that is attached here? Plus M or minus M?
Plus M.
Plus, because nitrogen is not attached to any electronegative element. It is attached to carbon, which is less electronegative, and also has a single bond and has a lone pair. What about chlorine here? Plus M or minus M?
Plus
M. Yes, okay, very good. Huh? I think now we can start. Now we can look at what is the effect of these group if it is introduced, and more specifically on the benzene ring. Okay, more specifically on benzene ring.
Sir,
What happens?
was my audio? Hello, sir.
Your audio is clear.
My audio is coming.
Yeah.
Okay.
हाँ, आयशा तो इतना परेशान रहती है, उन्हीं को पढ़ाना है. दिक्कत तो तब होगी जब मेरा ऑडियो नहीं है. Yes, Aisha, you always have chat. 29th, and this is
Yes.
Jan, and it is Saturday. Okay. So right next, plus M effect. So let us look at the example of OH group that is attached to benzene ring, an OH group that is attached to benzene ring. So I'm going to just copy this. It's going to help me. Okay. Now in this we have double bonds like this. There's a lone pair on oxygen atom. There's a lone pair on oxygen atom. What is going to happen? First of all, we have to identify that there is a double bond B, single bond C, and C has a lone pair. C has a lone pair, right? That is why there can be resonance in which the lone pair will go to this CO bond and then this pi bond will break, and the next carbon atom, it is going to get the pi bond. Then we can write the next resonating structure. So in this resonating structure, you will first of all make the single bond skeleton. And after making the single bond skeleton, you will first of all add the bonds which are intact and where there are no arrows, right? So these two bonds, and these are not having any arrows. Now we can see that one bond is being made like this. And obviously oxygen will get a positive charge because it was not sharing electrons. Now it is sharing electrons. Hence it will be getting a positive charge, right? And this particular electron that was a pi bond here, it has gone in this carbon atom. So you can either write lone pair with a negative charge or just a negative charge, both are fine. But whenever you are writing a negative charge, please understand that there is a lone pair of electron. Okay, there is a lone pair of electron. For example, if I write it like this, then you understand that there are two hydrogens here, right? Achha, just wait a second. Nobody is at my home and there is phone that is ringing. Wait a second, okay? I will be just back. Yes, sorry for that. But let's now move on to the next structure. So in the next structure, we can see, please don't go back, okay? So as you can see that we are moving this way. So we will be moving on this way only, right? So we are moving clockwise. So the electrons will be moving clockwise until and unless they come to their place once again. Until and unless they come to their place once again. Now, the electron movement will be something like this because we have A double bond B, single bond C, and C has a negative charge. That means there is a lone pair of electrons here. That means what will happen? This negative charge will form a bond here. This bond will break and it will go to this carbon atom. We can furthermore make a resonating structure. Again, all the single bonds. Then we will make the bonds that are intact, put the charges as they were in the previous structure, which has not been touched. And this bond has not been touched. Now this bond has been formed and there is a negative charge here, right? Now, again, I hope you all can see A double bond B, single bond C, and C has a negative charge, right? So we can again have some movement of electron from the negative charge to the next bond that is being formed. And this pi bond will go to this carbon atom. Now, there can be another structure which will make it like this. So again, single bonds. And here we have negative charge. And the new bond is being formed here. This bond is untouched. This bond is untouched. There is a positive charge here, right? Which is as the before resonating structure. Again, we have A double bond B, single bond C, and C has a negative charge. Now what we are going to do, we are also going to make one more resonating structure. This will form a pi bond here. This pi bond will break, it will go to oxygen and it will neutralize the oxygen. It's going to neutralize the oxygen. So we are going to make a OH pi bond here. These pi bonds are intact. And then you got the lone pair where it was present. So we started with lone pair on oxygen. We will have to make resonating structure in the same direction. So we started clockwise. So we went complete clockwise and we did the complete delocalization of the electron. And the electron is back to OH negative. That means these are the possible resonating structure for phenol, right? This is phenol. And the resonance hybrid will be something like this. So again, only the single bonds, no double bond as of now. And we will write a OH group, right? We'll write a OH group. Then we will look at OH and we will see that it has a delta positive, it has a positive charge in some of the resonating structures. That is why this will get a delta positive charge. And then we look at the next bond. So it is single sometimes and just sometimes double bond. And hence we will give it a partial double bond character. Now this carbon does not have charge at any of the resonating structure. That means it will be not having any charge. When I look at this bond, it is what? Partial. So all of these bond, I can see that they are partial double bond. So we can write it like this. And then I look at this carbon atom. So this carbon atom, it has sometimes a negative charge. So I will write a delta negative here. Then I look at the next carbon, that is this carbon atom. This carbon atom does not have any charge in any of the resonating structures. So I will leave that as it is. I will leave that as it is. I will not make any changes to it. Then I look at the next carbon atom. So I'm seeing that it has some delta positive, delta negative charge in some of the resonating structures, and that is why I give it delta negative charge. Then I look at the next carbon, it is not having any charges, so I won't touch it. I will leave it as it is. Then in the next carbon atom, it has a negative charge in one of the resonating structures. That means there will be a delta negative charge here. There will be a delta negative charge. So what I can say from these structures and the resonance hybrid structure is that in this substituted benzene, where we have attached a plus M group, we have increased the electron density at some specific spaces. So this has more electron density, right? So these are the places which has more electron density. And we know the names of these particular positions. This is ortho, this is para, and this is also ortho, right? This is also ortho. So we can say that the introduction of plus M groups, please write with me, introduction of plus M group increases the electron density, at ortho and para position. At ortho and para positions. Please write this down. Let me know if you're done. All of you understood this? Yes or no? Please tell me.
Yes, sir.
Okay. Yes, sir.
Done, sir.
Is there anyone who is still writing? Please let me know. Otherwise, I will scroll down to discuss the minus M effect. Done, guys? I think everyone is done. Okay. Next, we are looking at minus M effect. So for minus M effect, I'm going to take the nitro group, which is the most electron withdrawing group, the strongest electron withdrawing group, that is NO2. Okay, so we have nitrobenzene. We make the benzene structure. So first thing that will happen here is that this bond will move, right? Because we have A double bond B and A double bond B, single bond C, double bond D, right? So what we can do, we can make two type of structure. We can directly make a resonating structure, or we can go stepwise. So what I am doing right now, I hope we have seen, right, the resonating structures. So since you have seen the resonating structure, see here, once the pi bond breaks, what happens? We start the resonating structure. Okay, so we start the resonating structure, or we can do what? We can directly write the resonating structures, right? We can directly write the resonating structure. So what I'm going to do, I'm going to show you the movement of two electrons like this, right? So this bond is going to break, and this bond is going to, okay, move to this nitrogen atom, okay? So wait a second, let me just do stepwise. Now here what happens? So this bond is broken. So this will get a negative charge. Nitrogen will get a positive charge. And then what will happen? This is a bond here, right? This is a bond here. There are these bonds. Now, this particular nitrogen atom, it will take the electrons like this, right? And what is going to happen? Again, the single bonds. So we have made a double bond here. This is a positive charge here. There's a negative charge here. Now, since we have made a double bond with the nitrogen will not have any positive charge as of now. Then what will happen? This particular carbon, it lost its electron because this carbon atom, it had a pi bond. It here also has a pi bond. So this will get a positive charge. The other bonds will be as it is intact. Furthermore, you can see that we can form a bond like this. We can write another resonating structure in which we have a double bond here, a negative charge here, and then there is a double bond here, a double bond here, and there is a positive charge at the para position. We can write one more resonating structure, which this bonds move. So again, you can see, since we started clockwise, we are still going clockwise. So there's a double bond here, positive charge, no, not positive charge here. There's a negative charge here, and a double bond which is formed here, a double bond which is formed here, and then there is a positive charge here. So furthermore, this bond will move here, right? And then this bond will move here simultaneously. So we can write the last resonating structure. In which we don't have to do anything. Just put a double bond here, and there will be a double bond here, here, and here. And now we can make the resonance hybrid structure. So we'll have the benzene ring. Attached to it is the nitro group. So we don't want to see whatever is happening inside the nitro group because we are not concerned with the whatever is happening inside the nitro group. Okay, we are more concerned what is happening on the benzene ring. What is happening on the benzene? Electron density is increasing or decreasing. If it is increasing or decreasing, at which position it is increasing or decreasing. So what we will do, first of all, make a double bond here because I can see that there is a double bond character because some of the bonds are double bond in the resonating structures. Then when I look at all the carbon atoms and all the double bonds here, I can see that this particular bond is double bond here, but here it is single bond, here it is single bond, here it is single bond, here it is single bond. That means there is a partial double bond character in all of these bonds. So I've shown it like this. Then I see at this carbon atom has a positive charge, hence the delta positive. This carbon atom does not have any charge in any of the structure. That is why no charge. This carbon atom has delta positive. This carbon also has delta positive. So once again, we can see that the introduction of -M group has effect on ortho and para position, but the effect is that it is decreasing the electron density. So this is the ortho position, this is the para position, and this is the ortho position, right? So again, we can say introduction of -M group in benzene ring decreases the electron density at ortho and para positions. Ortho and para position. It means, what does it mean? It means that, please note it, mesomeric effect is not valid at meta position. There is no mesomeric effect at meta position. Okay, so if you look at the meta position, it does not have any effect. The +M or -M group, they don't have any effect on the meta position. Okay, so please write this down. Let me know if you're done.
Done, sir.
Okay. So this is something that we have written. Now let us try to look at what are the different order of +M and -M groups. Okay, so we know what effect does it has and where it has the effect. So increases the electron density, decreases the electron density, and at ortho and para position. But now let us look at the comparative order of the strength of +M and -M. Okay, so please write the topic. Order of +M. So in this we will be discussing the which of the +M group has most power to give electrons. So CH2 negative can give the most electron because it is low. It is low. It has low electronegativity. CH2. Let me just put a lone pair here and give the 9s sign here. Okay. So this has the highest ability to give electron through pi bond through resonance, followed by NH negatives. Right. So this has two lone pair NH negative. This will be followed by O negatives. I have to also make some bonds like this, right? It has three lone pairs, not because it has lone pairs. Okay. So as you can see, the number of lone pairs are increasing, but it doesn't matter because we know that the electronegativity of carbon is very low, and that is why carbon will be able to give electrons more easily than oxygen and then nitrogen. Okay. So this will be followed by NH2. Now, as you can see, we have written oxygen here, which has less tendency to give electron than nitrogen. But why it is giving more electrons? Because it is O negative. So a charged species, it wants to decrease its charge. So even though it is oxygen, it has to give electron. It has to give electron to lower its charge. Okay. So none of the electronegative element, it will take a negative charge due to electronegativity. Okay. Due to electronegativity. So again, you have NH2, which is a NH2, it is neutral, followed by NHR. This will be followed by NR2. This will be followed by OH. So now you can see, if I compare the neutral, so if you are comparing the charged species, you can see that oxygen is the least, right? Oxygen is at the least. If you are looking at neutral, again, oxygen is at least. This will be followed by OR negative. Sorry, OR with a lone pair, not negative. Two lone pairs on oxygens. This will be followed by NH C double bond O. R. So here we have this nitrogen, it is going to give electrons. Similarly, this will be followed by oxygen, the carbonyl carbon. There is R group. Okay, so it is reversed Easter group. So this particular oxygen, it has tendency to give electrons. Okay, so this is the order of plus m. This is the order of plus m. Let's write the order of minus m. Order of minus m. First of all, obviously, CH2 positive. This will be followed by NO2 in neutral, followed by nitrile group. This will be followed by carboxylic acid. Let me know if you're done.
Done, sir.
Done. Okay. So we have seen that if you have a benzene ring, and if there is a benzene ring, okay, and this has a group attached to it. So this group can be either plus M, then what happens? It increases electron density in ring. Okay, and if the group is minus M, what it does, it decreases the electron density in ring. Okay, so with this in mind, please write one question. Let us at least solve one question. Compare the electron density for following. Here you have simple benzene. Here you have OH group attached. This you have NO2 group attached. And here, let us say you don't have anything. Okay, or let us say you have CH3 because you have taken benzene. Yeah. So you have to consider at least two things that you have learned. You have to consider plus I, minus I, plus M, minus M. Okay, so plus I and plus M, they will increase the electron density. Minus M and minus I, they will decrease the electron density. And obviously, if you have any, first of all, you identify this. So in the A, obviously, you will not have anything because there is no groups attached here, right? There is no groups attached here. What about OH? Tell me, it will be plus M, minus M. First of all, tell me, will there be any plus M, minus M here?
Plus M.
Plus M. OH will be plus M. What about NO2?
Minus M.
Minus M. What about CH3?
Plus M.
Plus M. CH3 will not give you as such plus M, but I mean, we can talk about it in hyperconjugation. But right now, I can say that it will give you me plus I, right? Yes or no? Tell me, Mariam.
Yes, sir.
As of now, we can say that because it does not have any lone pair. So how is it going to contribute into resonance? So from here, we can clearly see that B is the winner, right? Because if we have to compare plus M and minus I, or plus M and mesomeric effect and inductive effect, then obviously mesomeric effect is the winner. So we can compare and we can get the answer just by mesomeric effect. There is no issue of the inductive effect. There is no question of inductive effect, right? Comparing them. So B is the winner. B has the most, followed by, so we will first of all talk about the plus M and plus I, right? So B has most, and then we have D because it is also a plus M, plus I group, sorry. It is also electron donating group, followed by, now we have to compare. Here we have no effect. That means there is no disturbance in the electron density, and here it is decreasing the electron density. So obviously A will be going to the next, and then followed by C because C will be the least, because in A there is nothing happening. In C you are taking away the electron density. So obviously C has the least electron density. Okay. So write this down. Then we will look at hyperconjugation.
Done, sir.
Done, sir.
Done. Okay. Right, next, hyperconjugation. Hyperconjugation. First of all, let us write the definition. This is the delocalization of sigma CH bonds, sigma CH bond CH bond electrons with pi bond or positive charge or free radical is called hyperconjugation. It's called hyperconjugation. So there are three things that you have to remember. Either there should be a pi bond, right? There should be a pi bond, or there should be a positive charge, or there should be a free radical. Okay, or there should be a free radical. Now we can summarize rather than remembering these three things. What you can see is that you can just take example, right? CH2 double bond, CH2. This is a pi bond. There is a pi bond here. And if I take CH3 positive, so there is a positive charge here, right? So we have an empty orbital. And if I take CH3 free radical, so these are the three cases. Now what is common in all of them? The common thing in all of them is that one of these carbons, right? If you have a double bond, then you can see that this is what the steric number here is. How much? Tell me guys, steric number is how much here? What is the steric number here? You guys remember steric number? The word, at least the word, yes or no? Mariam, Reba, Sara, Surat, Abhinav. Steric number?
Yes, sir.
What is steric number? भूल गए. Acha, you tell me the hybridization. Forget the steric number. If you can tell me the hybridization, we'll have no issue. Tell me, what is the hybridization here? What happened? What is the hybridization? Okay, no problem. Steric number is number of sigma bond plus lone pair. Tell me, what is the steric number on the carbon?
Four,
How many sigma bonds are there?
3,
And how many lone pair?
no lone pairs.
So three. Steric number will be 3, now, not 4.
Yes, sir.
So what will be the hybridization? Tell me. sp2, bhai, hybridization. Please don't forget hybridization, guys. Listen, at least remember these. Steric number, if the steric number is 2, it is sp. If it is 3, it is sp2. If it is 4, it is sp3. These things will be helpful in organic chemistry. Please remember these, okay? You cannot forget this. Okay? And here also you can see that steric number is 3, so the hybridization will be sp2. Here also you can see that the hybridization is how much? sp2. So rather than saying that it has a pi bond or a positive charge or free radical, we can put up a condition. That the hyperconjugation is happening only if we have at least one sp2 hybridized carbon atom. Okay, at least one sp2 hybridized carbon atom. Let's write the conditions. What are the conditions for hyperconjugation? So in hyperconjugation, you should have at least one sp2. Am I audible, guys?
Yes,
Hello?
sir.
Okay. This is fine. At least one sp2 hybridized. carbon atom. Okay. Second is that there should be at least one alpha carbon. At least it's a one hydrogen, alpha hydrogen, one alpha hydrogen with respect to one alpha hydrogen with respect to hybridized carbon atom. Okay. sp2 is carbon atom. So what is alpha hydrogen? For that, you have to remember what is alpha carbon. Alpha carbon means adjacent, that is next carbon. Okay. Alpha carbon means next carbon, and the hydrogen is attached to alpha are called alpha hydrogens. Are known as alpha hydrogens. So write the condition down, then I will ask you about the alpha carbon and alpha. Done, guys? Hello, are you done?
Done, sir.
Done. Okay. So I'm giving you some questions. You have to identify which of the carbon is alpha carbon, and then we can just count the. First of all, you have to identify the sp2 hybridized. Then only you can identify the alpha carbon. So it is important that you should remember alpha means alpha hydrogen. That alpha carbon means the adjacent or next carbon with respect to what the sp2 hybridized atom. So first of all, you have to identify the two, and then you will look at the next carbons. Okay, next carbons to it. So let's write the first question. Okay, so I'm just numbering A, B, C. Okay, so you will have to tell me which of the following is sp2 hybridized and which of the carbon is which of the carbons are alpha carbons or alpha carbon. That's it. 4 questions are enough. First of all, you tell me, okay, what is the sp2 in the first question? Which carbon is sp2?
B.
A.
Which one?
B.
B. Yes, Sarah, correct. That is B. And what are the alpha carbons?
A and C.
A and C. Okay. And then what about how many alpha hydrogens? Tell me the number of alpha hydrogens in the structure. How many alpha hydrogens are there? So how many hydrogen atoms are attached to these alpha carbons? You just count them and tell me. In the alpha carbon, how many hydrogens do you have?
6.
Yeah, correct. 6. What about the second question? Which one of them is sp2, A or B?
B.
B. And how many alpha hydrogens? Directly tell me how many alpha hydrogens?
1. Oh, 3.
3. Okay. What about here in the third question? A, B, C, D. Which of them is alpha? Achha, wait a second. What happened to others? Why are the others not answering? Yes, Reba, Surat, Abhinav, Mohammed Umar, you came just now. Najib and Mohammed Sheikh. Yes, what happened, guys? Aisha? Ari, no one is replying. Are you guys not present? Yes, tell me for the third one. Which one of them is sp2?
B and C.
Yes, very good. B and C. Okay, Aisha, okay. What about how many alpha hydrogens here?
6.
6. What about the fourth structure? Which of the following is sp2?
A.
Okay, and how many alpha hydrogens are there?
6.
You have to now. This is something that I think all of you are lacking. How many hydrogens in the bond line structure you don't know to calculate directly?
4.
I just hope that you should be acquainted with this, man. Why you are taking so much time? Okay, 4. Bond line structure is the thing that you have to learn. Okay, there is no other way. There's no other way. Okay, fine. So this is done. Like you can identify where you have hyperconjugation and how many alpha hydrogens are there. Now let us see what happens in hyperconjugation. What happens in hyperconjugation? So wherever we have sp2, wherever we'll have sp2. So we have a carbon atom which is attached and it has 2 bonds. Let us say this is H and this is also H, and it will be attached with some other bond. There is a positive charge, let us suppose. That means there is a pi bond, sorry, pi orbital, which is vacant, right? There should be a pi orbital. Sorry, there should be a p orbital, which is vacant like this. Here. This is vacant, and here you have CH, right? All of these are CH. So for some time, what happens? For some time, what happens? These electron pairs which are here now, and since this is positive charge, so all of these hydrogen CH bonds, they will be somewhat attracted towards the positive charge. So for a fraction of times, what happens? For a fraction of times, what happens? The electron pairs which are here, and again, it is a wave. It is not like it has a wave particle duality, so it can behave as wave. And what happens? Some of the electron density it moves towards this particular carbon atom, and since one of the electron is moving here, what will happen? It will make a double bond like this. And this H will be having H positive. So as you can see, there is a bond broken, and that is why it is also known as, these are also known as no bond resonance. These are also known as no bond resonance. Now, since this H plus has broken, now again, this is happening again and again, okay, so this is happening again and again. So this is how a particular carbocation can also get stability through hyperconjugation. Now, since here in this structure we have 3 hydrogens, so all of these hydrogens can one by one take part in hyperconjugation, and we can get 3 structures. As we have drawn one structure from this hydrogen, we can draw 2 more structures using those hydrogens. So in this, as we can see, there are 3 alpha hydrogens, and hence 3 hyperconjugating structures are formed. So we will write number of hyperconjugating structures is equal to number of alpha hydrogens. Okay, is equal to number of alpha hydrogen. And since as we are making a bond with a carbocation, and that means the positive charge of this plus this carbon atom, it is getting decreased for a while. That means hyperconjugation is giving stability to carbocation. So hyperconjugation stabilizes carbocation, free radical, and also alkenes. If I will have to compare the stability and also alkenes. Okay, and stability will be directly proportional to number of alpha hydrogens. Write this down. Let me know if you're done.
Done, sir.
Done. Okay. So we can do a small question on comparison. So in the first question, we have to compare CH3 positive versus CH3 CH2 positive. Okay. So in this case, we can directly say that CH3 CH2 positive is more stable. Why? Due to three hyperconjugating structures, as there are three alpha hydrogens, right? There are three alpha hydrogens. Secondly, we can also compare. So this is also what? This is also a 4 carbon, which has a double bond, right? Which has a double bond. We can compare this with if you have something like this. Okay, now since all the structures are same, right? Everything is same, all the fragments are same, but only there is a difference in the position of double bond. So for these two alkenes, we can compare the stability. We know that these carbons are sp2, and here this carbon and this carbon is sp2. Now if I look at the alpha hydrogens, so this is cs3 here, this is also cs3 here. So in this case, we have alpha hydrogen, which is equal to 6, but in this case here we have only 2 hydrogens, right? Because this is only the alpha carbon, and here the alpha hydrogen is equal to 2, and hence this will be more stable, right? This will be more stable, right? This will be more stable. You can also write CH3 free radical will be least stable, followed by CH3, CH2 free radical, followed by CH3, CH, CH3 free radical, and followed by CH3, C free radical, which has 3 CH3 group attached. So in this alpha hydrogen, it's equal to 0. Here the alpha hydrogen is equal to, this one is equal to how much? 3. Here the alpha hydrogen it is equal to 6, and here the alpha hydrogen it is equal to 9, right? This is equal to 9. So write this down. I hope you understand the stability now of and how to answer it with respect to the hyperconjugating structures. What happened? These two things are okay. Write this down. Let me know if you're done.
Done, sir.
Then all of you, what about others? Yes, others. Reba, Sara, Surat, you're done? Yes or no?
That's
Done? Okay, fine. So next, sorry. Okay, so in the next class, we will be studying about the next class we will be studying about how to compare the stabilities and how to compare the stability of carbocation, carbanion, and carbon free radical. Okay, and we will be using all the electronic effects that we have studied till now. That is the inductive effect, right? The mesomeric effect or resonance, and the hyperconjugation. So with these four, we will be talking about the stability of carbocations and whether which carbocation is going to be more stable. So we have looked at some ideas here. Here we have looked at free radical alkenes. Alkenes we will not be studying because we will be learning more about intermediates, but the stability of alkenes, it will be useful when we are going to learn about the chapter hydrocarbons, and we are going to learn about the section alkene. So we will meet tomorrow, and hopefully this chapter will be completed while after we are done with the comparisons. After we are done with comparisons, now you guys have two choice. Okay, now you guys have two choice. Acha, nahi. Everyone will be there now. So nahi. Saturday, Sunday. So next Saturday, I will be starting hydrocarbons. Okay. So all of you should be present. Okay. So this is in term 2. I hope all of you know this is in term 2. So no more term 1. Term 2 hydrocarbons will be started. Okay, hydrocarbons will be started. So what I was thinking that those who want to learn about term 1, we can teach them after the syllabus is complete, and if you have time with your examination. So keeping that in mind, we will start first of all hydrocarbons, and this chapter was important. Or if I look about the term 1 portion which has left, which is hydrogen, right? And there is one more chapter which is redox, right? So hydrogen, I hope that you can cover it even if you just look at the periodic properties chapter. Okay, it does not need much attention here, but redox reaction also has one part that is balancing. That I think is important, and that I think you will be needing. So what that can be done later. First of all, we'll start with hydrocarbons. Let's get done with the term 2 syllabus. Then we can talk about hydrogen and redox reactions and the balancing part. Okay. So next Saturday will be hydrogens, but tomorrow you have a class, same time. And this will be the last class of this chapter, that is organic chemistry, some basic concepts and techniques. So let me stop sharing my screen. Thank you very much. We'll meet tomorrow. Assalamu alaikum. Goodbye.
So,
Good night. Take care. Haan ji, boliye.
Sir, will we do hydrocarbons on Saturday and Sunday only?
जी हाँ. अरे आप हैं कौन से बैच में? आप कब आती हैं? मंडे वेंसडे ना?
Yes, sir.
मंडे वेंसडे तो आती हैं, लेकिन कितने बजे आती हैं आप?
7 to 9.
7 to 9. अच्छा, अगर आपको हाइड्रोकार्बन शुरू करना है तो आप ट्यूसडे को आप 9 से 10 भी आ सकती हैं. वहाँ भी
मतलब जो
हाइड्रोकार्बन,
मेरा नॉर्मल बैच है उसके साथ.
हाँ, जो उसके साथ जो एक्स्ट्रा, आप एक बैच में आपका नॉर्मल चलता है, दूसरे में आप एक्स्ट्रा क्लास कर रही हैं. ठीक है, तो आपके पास दोनों चॉइसेस है. लाइक आई मीन दिस इज फॉर ऑल ऑफ यू. If you want to come on Tuesday also, then also we can start hydrocarbons. Or if you are okay with the Saturday, Sunday, then we can do here also. Okay, fine.
तो फिर मंडे एंड वेडनेसडे को क्या पढ़ाया जाएगा? लाइक हाइड्रोकार्बन नहीं पढ़ाया जाएगा ना?
क्या पढ़ाया जा रहा है मंडे वेंसडे को? आप बताइए क्या चल रहा है?
इक्विलिब्रियम.
हाँ, इक्विलिब्रियम चलेगा जब तक खत्म नहीं होता है ना?
ओके सर.
ओके, एस और पी ब्लॉक भी है. माना कि छोटे चैप्टर से सारा सिलेबस हटा दिया गया, लेकिन वो भी है, उसको भी खत्म कराया जाएगा इंशाल्लाह, है ना? सो दोस चैप्टर्स आर आल्सो देयर. डोंट वरी अबाउट एस एंड पी ब्लॉक, है ना? वी विल डू दैट 2 hours, and I think both the chapters will be done in 2 hours. Okay, 2 hours for S block, 2 hours for P block. Fair. Thank you guys. Any more questions? No questions. Okay, fine. Chalo. Thank you. Bye bye. Take care.
Bye, sir.
Thank you sir.
Bye.
Sir.
Bye bye. Allah Hafiz. Assalamu alaikum. नहीं, Muhammad Umar. I will solve only when your mic is working, because how would I know that you are understanding or not? You know that I will ask you questions, na? So maybe tomorrow. Can you wait till tomorrow? Muhammad Umar, in the chat. You will reply in the chat. Acha, fine. So let us do one question because we have students from the next batch. Okay. So one question and drawing from name. Give me a name if you have a particular name. Okay, I've got your 4-ethyl, 2-methyl, hexane. So whenever you are going from name to structure, the first thing that you will do is parent. Okay, so what is the parent? Hex. So you'll have carbon, that is how many carbons? 1, 2, 3, 4, 5, 6 carbons. Second, you will look at the functional group. Hai. That means you have to take care of the numbering part. Whenever you are doing the functional group, that means you are taking part of the numbering part. Okay, so hexane, that means no functional group. Third is unsaturation. So unsaturation is ane, so we don't have to worry about that also. And then you will look at the substituent. So you have 2-methyl and 4-ethyl. 2-methyl. So you can put 2 here, CH3, and 1, 2, 3, 4. And here you can put C2H5, that is ethyl. Then you can put the hydrogens elsewhere. Yes, Muhammad Umar, got it? Okay, so I can number it from anywhere. I can number it 1, 2, 3, 4, 5, 6 like this. Also, I can also number 1, 2, 3, 4, 5, 6. Right now, you can choose any of the numbering. It doesn't matter, but you have to choose any one. Okay. Any other Nina? I mean the time is.